So the proof of this theorem, based on our previous computation of the higher order derivative of our function phi here, we can easily prove this theorem. Compare the theorem and the expression of the phi lt here. We notice a slightly difference here, because the higher order derivative of f, we use the D notation, but in the theorem we use the sub-index notation to denote higher order partial derivative. They are equivalent, but the sub-index case saves some space because I don't need to write the D notation. Okay, so this will save some space because the formula is so long. If every turn I have this D notation or this partial notation, the formula will be much longer. Therefore, we use the sub-index notation. But this is the same. So in the expression of phi lt, we can also use the, for example, here we can also use the fj1 jl. Okay, then it will look much better. Okay, now we prove the theorem. So this is our omega. This is a plus h. Okay, so as before, consider this function phi t is f a plus t h. Okay, then we have computed the derivative phi l t is f j1 jl a plus th hj1 hjl. The multiplication of the j1 component of h, j2 component of h until jl component of h. Okay, so this is true for L not greater than k. Therefore, applying the single variable Taylor formula to our phi, our fa plus h is phi 1. So phi, the single variable Taylor expansion phi t is sigma k minus 1 I from maybe L 0 phi L 0 t to the power L, then k phi k 3 tau t to the power k. This is the single variable Taylor expansion. Now let t equal to 1 in this formula, we will get phi t is sum k1 minus 1, L is 0. Phi L 0 is f j1 jl a, right? And h j1 hjl. Okay, phi L 0 here. For this, you let t equal to 0 in this formula, you get this. Okay, so, and also the last term is plus k and phi k tau. Phi k tau, that is f j1 jk L equal to k a plus tau h hj1 hjk. Okay, So this A plus tau H, because tau here is between 0 and T. In the single variable Taylor, the tau here is in 0 and T. But now our T is 1, so our tau is 0 and 1. So A plus tau H is a point lies here. A plus tau H. This point we denoted by Xi. Then this is Xi. So this is the result of our Taylor expansion. Okay, but in the statement of the theorem, I write every term, and for the proof, to save space, I use the sigma summation. I use the sigma for L here. But the result is proved. Okay. So this is an exciting result. We have generalized the complicated Taylor expansion beautifully to the multi-variable case. Okay. We also need a piano remainder version of the Taylor expansion. So this was stated as a corollary. Because piano expansion is considered the case H goes to A. H goes to 0. Therefore, this is a local result. Only concerned the behavior of the function near the point A. So we only assume that f is defined in the neighborhood of A. So let f be a ck function defined on some neighborhood of the point A. Then, as h goes to 0, our fa plus h equal fa plus fia hi plus 2 fija hij plus k fj1 jk a hj1 hjk plus a remainder term we denote by little o of the case power of the norm of h. This means if you denote this by eta h, or if you like, this is the classical notation. Or if you like, you can write this as eta h, where eta is a function such that h goes to 0, eta h divided by is 0. Okay, so this is the piano remainder term. The eta is a piano remainder. So this is a corollary of the previous theorem. So the proof is also very easy. You want to prove that the remainder term eta, you want to prove that for some eta this equality hold. So obviously that this eta h must be the left hand side minus the sum of all the terms except the last term of the right hand side. I write this down. Eta must be the difference of left hand side and the sum of right hand side, except the last term. Okay, so remember this. This is obvious. So the result we want to prove is simply the left hand side minus the other term of the right hand side. So we need to prove that fa plus h minus the other term, we can use the summation. L is 0. L f j1 jl a h j1 h jl. So the sigma sum is the sum of all terms on the right hand side except the last term, our eta. So the corollary is to the conclusion of the corollary means that this difference divided by the norm of h to the power k should go to 0, converge to 0. If you can prove that this converges to 0, then the corollary is established. Okay, so to prove that this is converging to 0, we take absolute value. We need to take absolute value. So we take absolute value. Take absolute value and apply the previous theorem to the fa plus h. For this term fa plus h, we apply the theorem of the conclusion of the theorem. So fa plus h is the sum of fa plus h here is the sum from L from 0 to k minus 1. Okay, but now we are subtract by L from 0 to k. So every term for L equal to 0, L equal to 2 until L equal to k minus 1, every term cancels except the L equal to k. For the a plus h, there is also a term for L equal to k. This term is the same as this as the L equal to k term here, except that here the higher order derivative is evaluated at a, while our fa plus h here, it is evaluated at c, or a plus tau h. Okay, so from this comment we see that this will not greater than fj1. Maybe we have we also have k hk and f j1 jk a kc minus not kc a plus tau h. Of course, this is our kc minus f j1 jk a, the absolute value of this. Then the hk1 hj1 hjk. Okay, so this two part can is less than 1. The every hj divided by the norm of h obviously is not greater than 1. The absolute value, we also have absolute value here. Outside this, we also have absolute value. So obviously this is not greater than 1. This is not greater than 1. So this using this fact, this k, the multiplication of this k term can be cancelled with the the norm of h to the power k in the denominator cancel. And for the absolute value here, fj1 jka plus tau h minus fj1 jka, since h goes to 0, we are talking about how the function behavior as h goes to 0, right? Therefore, our h is goes to 0, but our f is ck. The case order derivative are continuous, so this is a continuous function. For every j1 jk, the corresponding f j1 jk is continuous function. So as h goes to 0, the absolute value goes to 0. In conclusion, everything together goes to 0. So this proves that this goes to 0 as h goes to 0. So this is the conclusion of our corollary.